Welcome to Summarize Science. High-energy physics has always been a field defined by years of grueling manual labor and complex computer programming. Recently, researchers developed a new framework called Just Furnish Context to see if AI agents can autonomously perform these complex experiments. This diagram shows the massive difference in speed, taking a process that usually takes a year and shrinking it down to just 3 hours. On the left, we see the current human-driven world, and on the right, the streamlined AI-assisted workflow. While previous AI tools were restricted to simple tasks, this new framework allows agents to plan an entire analysis from scratch based on a simple prompt. The JFC system is built on top of Anthropic's Claude Code and uses specialized sub-agents for execution and review. The system breaks the physics analysis into sequential phases, starting with the strategy and ending with the final documentation. One of the most critical features is the ability for the AI to retrieve and learn from a vast corpus of prior experimental literature. To ensure accuracy, the framework uses a hierarchy of reviewer agents that simulate the rigorous internal review process of a real physics collaboration. These bots perform programmatic sanity checks on data, validate plotting code, and flag any errors that might occur during calculations. Crucially, the system includes a human gate that requires a real physicist to approve the results before the AI can proceed to the final step. The researchers tested this framework on multiple real-world datasets, including measurements of the Z boson and the Lund jet plane. They even tasked the AI with measuring the number of light neutrino generations using over 3 million events from the Delphi energy scan. For more advanced challenges, the agent extracted strong coupling constants and measured complex jet substructure variables. The results suggest that while humans are still needed as architects, a huge fraction of technical work can now be automated. This could fundamentally change graduate training, allowing students to focus on physical intuition rather than debugging code for months. There are still limitations, such as a complexity ceiling where AI might struggle with truly novel techniques or multivariate analysis. Moving forward, the field will need standardized benchmarks to evaluate how well these AI physicists are actually performing. The technology for student-level physics analysis is effectively here, and it is largely built on top of existing language models with clever prompting. By looking at specific measurements like the Z boson line shape, we can see the level of detail the AI is capable of handling. The AI agents were able to accurately model background fractions as a function of energy, a task that requires deep domain knowledge. This chart shows the measured cross-sections of the Z boson line shape produced entirely by the agentic workflow. Here is a two-dimensional Lund plane density map, which the AI constructed from millions of primary declusterings in the data. The AI even generated its own correlation matrices to show how different data points relate to one another. Finally, the agent was put to work on Higgs boson signal strength measurements using data from the Large Hadron Collider. It successfully produced post-fit data comparisons that align with expectations from the standard model of physics. To recap, these researchers have shown that AI agents can now autonomously plan, execute, and review complex experimental physics. This means a massive increase in scientific throughput, as tasks that once took months can now happen in hours. It also opens the door to remining decades of old data archives to see if previous experiments missed any subtle clues about the universe. Ultimately, this technology does not replace the physicist. It frees them to be the creative thinkers that drive science forward. Thank you for watching Summarize Science, and stay tuned for more breakthroughs in the world of physics.